In this practice problem, we have a bicyclic ester, a diester, I should say, and we're asked to, 1, predict the products, and 2, predict the mechanism. So let's actually go through the mechanism first and then predict the products. It's going to help us a lot more. So what do we know? Diesters, you could also call them acetals, and we learned through our organic chemistry course that acetals can undergo hydrolysis. So I'll just draw a simple little thing here. We have a ketone and acetals, and I am asked to interconvert between an acetal and a ketone. How would you go about it? Well, we know with an acid, say H2SO4, and let's use our acetal, and we'll call that ROH. Okay, we use acidic conditions in ROH, ROH meaning our alcohol, where you're going to get a acetal. But if we instead swap out the acetal for H2O, and we also use acidic conditions, well, we're going to get our ketone right back. And in this case, we have acidic conditions, H3O plus and H2O. So what do you think is going to happen, right? If we have a acetal, it might not look like it, but notice off of this carbon there's an oxygen in R groups and an oxygen in R groups. So it is an acetal. So acidic conditions, we're going to go right back to a ketone, right? So let's show how that works. Okie dokie. So it begins as such, and we'll draw the mechanism because predicting the products in our head can be kind of tricky. So let's use some acid here, and you could go either way. You could protonate this oxygen, right? Because oxygen is the species that has lone pairs on this molecule to actually pick up a proton, and it could be either of them. But let's just say it's the top, and I think that this is the easier way to see the molecule. So we're going to neutralize that into water. Okay, so we have this acetal here. So what comes next, right? Well, water isn't going to want to attack there just quite yet. We know that the mechanism for this, right, if we just have a generic acetal, so we have our ORH and OR, we know that what's going to happen here is this group is ready to leave. So our oxygen here is going to fold in and kick off that group as a alcohol leaving group. Now, in this case, since we're stuck in a ring here, it doesn't quite leave the molecule, but it leaves that section. It gets kind of broken off, right? Take a Lego piece and snap it off. That's a way that you can view this. So these lone pairs here are going to fold in, and this is going to help that oxygen leave. It's a more favorable process. So we are going to get an OH here, and we said here we have double bonded oxygen, which makes this oxygen positive. So let's kind of redraw the structure here so it's not such an eyesore, and let me just make sure you guys can see. Okay, let's draw this, and how many atoms in the ring do we have? 1, 2, 3, 4, 5, 6. So let's draw this as a flat linear structure. So this is 1, 2, and then the double bond should go here, positive charge here. Okay, so that's what we have so far. Now we need to make this oxygen happy, right? This one was angry, it got woken up, and now this one is ready to go as well. See, it has a positive charge. So what can we do? Well, we have some water molecules. Remember, ketones, this carbon here is especially positive. When the oxygen, it has a positive charge on it, it's not a happy little oxygen, right? So what it's going to do is it's going to favor an attack on this carbon, right? So it can steal the electrons from the pi bond. So water comes in and attacks that carbon. So we actually get this molecule here, or this intermediate, I should say. I keep forgetting to draw that oxygen first. All right, so we get this. And now this oxygen's not happy. So how do we make this oxygen happy? Well, another water molecule could come in. It's like a little chain reaction. It's like one oxygen makes one oxygen angry, and then that angry oxygen makes another oxygen angry. And that's exactly what's gonna happen again. So some basic species here could pick it up. That's an oxygen, right? It's not gonna be happy to take it, but it's kind of like, they're playing hot potato. They're throwing around the hydrogens here. So water can pick up a hydrogen to make hydronium, reform our catalyst, right? So we have OH, O, and OH. Okie dokie, so we have this here, and if you notice, we now have an alcohol next to an oxygen here, and we know that for an ester, we would expect for this to break off, and we can actually do that here if we have H3O+. Remember, acid cleavage of ethers, that reaction. So we'll just use protic species here, so preferably our acid, it's more unstable, and it's going to unhappily steal a hydrogen, playing hot potato once again. So now this has a positive charge, and our alcohol is ready to push that group out. So what it does is it folds in these electrons, right? So this has the positive charge, and this oxygen's like, hey, I'm angry. Someone else, I'm gonna make you more miserable. So it looks at this hydroxide group and it's like, you're miserable now, and it kicks it right off. So this becomes neutral, this becomes positive. So let's draw a product here, and whoa, this mechanism's getting quite long. So I like to first draw it just with the bond broken to figure out where everything is, and then I draw a linear structure. So we have an OH here, and then we have, and it's always good to count your carbons to make sure you didn't add or remove one. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So yep, that's correct. Let's keep it like this before we present our final structure, just because this step is a simple deprotonation. So our molecule, we want it to be nice and happy, so we have a carbonyl here. So water comes in and is like, you can be a happy little carbonyl, and I'll be the miserable hydronium acid catalyst. So now that we have our structure, let's present it in a linearized format. So we have water, carbon here, we have an OH, and we come down to this carbon over, so wait, we go 1, 2, 3, another carbon here, and a carbonyl aldehyde. And so that's your final product here. That's what we would have predicted up there. Let's give it a name, why don't we? Just for more added fun. So how many carbons do we have? We have 1, 2, 3, 4, 5. So this is a pentane. We start numbering from right to left because our aldehyde is on the right. This is a dihydroxy compound. So we'll write this as 4, 5. And I don't care about chiral centers because, you know, we didn't really specify that. 4, 5, dihydroxy, pentane, and we drop the E, we replace it with a L. Oh my God, this problem was a fucking nightmare. So our bicyclic product, we go from that bicyclic looking thing to 4,5-dihydroxy pentanal. So hope you guys enjoyed. I'll move out of the way quick so you can review here. I hope you guys learned something. If you did, drop a like or a comment. Have a wonderful day. Goodbye.